311 is brought to you by Lego Harry Potter. We've got the little lightning bolt on his head. Oh, you can't see that. It's too blurry. Okay. So, 311, we're going to keep looking at logarithms and notice some special properties about them. So, first off, we were looking at the bouncing of an elastic ball, and it had this height that was bouncing that was diminishing over time. So we've collected some data here for ourselves using timers and calculators, whatever. We're just told we collected this data. So does the data seem reasonable? Number of times the ball hits the ground after distance traveled. So 6 times of 21 feet, sure. Yes, it does. It does increase, like our initial distance. That's 9 feet. And then we only increased by, what, 4.5 feet, and then a little bit less, a little bit less, a little bit less. That does seem to look like what's happening here. So let's toss these data into Desmos real quick and see what kind of picture we get. Okay, so in Desmos, of course, to create a table, you click the plus sign in the table, and we're just doing 1, 2, 3, 4, 5, 6. And then our other values, 0, 9, 13.5, 16.3, 18.7, 21. Remember that this little plus sign is a very useful thing. There's our zoom fit. Wow, that looks like a nice logarithmic function. Let's just find it for fun. This was part of one of your projects, so we're going to use the natural log as our way to find it. We're going to use y1 tilde a plus natural log of x1. Let's see how that looks. We'll go to log mode. Wow, that looks terrible. Let's get rid of the plus a, and let's do a product. Hey, that's not bad. Notice our a here is 11.8375. That's pretty close. So let me double check our data. 13.5, 16.8 points. Yeah, we're all good. Okay. We're told by our textbook that the data can be modeled by log base 10. So we could go back here and just try log and see what we get. I don't know, is that any better than the other one? 0.9964 for r squared versus 0.9964, same thing, right? So here's what our textbook says. Use y equals 26.75 times log of n. I'm going to use x's and y's here. So there's our other model. They're basically the same. It misses a couple of these points a little more than the other, so we'll be happy with that. So we verified that. Looks pretty good. It definitely is a reasonable model. And then our textbook asks us in number 5 to find 2, 5, and 10 bounces. So what I'm going to do is change this to f of x. And then I'm going to add in a table. In my table, I'm going to write f of x2 because I've got an x2 here, and I'm going to type in my 2 first, and then my 5, and then my 10. And those are the values that we're being asked to find. So running those values to 2 decimal places, we get 8.05, 18.7, and 26.75 for each of those. All right, on to the next page. So now we're asking, how are those values for n equals 2, 5, and 10 related? What's the relationship between those values? So let's look very closely at them. I'm going to rewrite them from the previous page. So we had 8.05 for 2, 18.70 for 5, and 26.75 for 10. And let's just take a look at what's going on for each one. So, So our textbook gives an interesting answer. They're saying it's t evaluated at 2 plus t evaluated at 5 equals t evaluated at 10. Does it really? Let's check. Would we have noticed that without using without the answer from the textbook? Maybe, if we had done it carefully. So notice I'm doing 18.7 plus 8.05, and that's going to equal 26.75. That's true. In other words, we're saying that 26.75, which was our initial model given to us by the textbook, times log of x. So when we did log of 2, so 26.75 times log of 2 plus 26.75 log of 5, that's equal to 26.75 times log of 10. We should not be surprised by this fact. Well, we're going to develop the property that connects this 2 and this 5 and this 10, and maybe you're seeing it. 2 times 5 equals 10. So when we're evaluating log of these of numbers whose products are equal, then the sum of the results of the logarithm is the same. So it says, using results from part B, how would you determine the total rebound distance after 10 bounces? Well, you'd evaluate log of 2 in our model and log of 5 using our model, and then add those results together, and we get log of 10. In other words, we have this listed out here in your textbook. And what this is showing is if we take this whole thing and we divide this entire expression, and we divide everything by 26.75. And this is a valid thing because we're dividing both sides of the equal sign by the same thing. So all this cancels, and we're left with log base 10, common log of 2, plus log of 5 is equal to log of 10. And just maybe to help us note some things, we could also write this 10 as 2 times 5. That's more or less what I was stating before. So we're getting really close to a nice definition of a property of logarithms. In fact, here it comes right here. It says if we have two positive numbers, a and b, then log base b of the product is equal to log base b of the sum, individual sums of each, provided that our b values are the allowed values. So let me rewrite that. This is the product property of logarithms. And it states if we have log of any allowable base, remember those allowable bases are numbers greater than 0 and not equal to 1, those two conditions on our b, of a product of two numbers, and our textbook said they both have to be positive. That's true, right? We can't have a negative value in here. So the reason we have to state this is we could have two negative numbers in here. So we could have done -2 and -5. That's positive 10. But if that were true, then this statement would not be true, that log of the individual ones added together is equal to the product. That's because we wouldn't be able to evaluate this if a was a negative number. So as long as everything's positive, this statement holds, and it's the product property of logarithms. It's a useful little property. Some other special words we use here. We call this left side the condensed side, and we call this right side the expanded side. And depending upon what we're trying to do, one or the other sides might be more useful to us.